Hello and welcome back to the lab. Today on the bench we have some storage. Actually, we talked about storage in a previous video. This is in response to a question that I got from a viewer recently. The specific question was, how do I become a tube technician? I am by no means an expert on this subject. I do work on vacuum tube equipment, but I am still learning myself and probably will continue to do so until they put me in the ground. So I am not an expert, but I have fixed some tube gear and I do have some experience repairing tube equipment. In that context, I'm going to try to answer the question as best I can. There are definitely some more authoritative figures out in the wide world of YouTube than myself, but we're going to give it a shot, and I'm at least going to give my perspective on the question, and we'll go from there. With any process, becoming a technician, engineer, master craftsman, however we want to label it, always start with basics. You fix more stuff going back to the basics than any of the nuance engineering things. Typically, if you're not building a circuit from scratch and you're repairing something, it's pretty safe to say it's worked once, unless you're doing the first assembly. So having assumed that it has worked, if it's coming across a bench, it is broken. The basics would be, if it was a radio, do you understand the function of a 5-tube radio? Do you understand the function of a scope? Do you understand the function of a TV? Not just how the tube itself functions, but how the signal gets decompiled and split apart into its various components. Because, I mean, in a TV signal, you have the video. Well, let's take color TV because that's a pretty complex signal. You have timing, you have color, you have intensity modulation, you have audio, sometimes mono, sometimes stereo, sometimes quadraphonic, sometimes 5.1, depending on the way it's receiving. You wouldn't find 5.1 in tube gear, but quadraphonic was around when tube stereo was still pretty big. I don't know if they ever did quadraphonic broadcast TV. Probably not. So understand the signaling. What do I need to put in, and what should I get out the other side? One of the first things we do as a technician is verify the fault. A lot of times it can be user error. The user's putting in garbage data and is surprised when garbage is coming out the other side. That's true for digital communication systems, high-speed digital, computers, TVs, radios. If it's not getting the right signaling, it's never going to work right. So understanding the source, well, really source to display, end-to-end, for whatever specifically is you're working on. I'm still bending my brain a little bit around stereo FM and getting the gear set up right and things like that. So if anybody has any pointers onto where to go to figure out how to set up gear to do FM alignments, let me know. I'm still digging that up. That one is twisting my head in knots at the moment. So that's what we're trying to figure out. After the basics, learn a bit of the hazards. I do hit safety a little hard on the channel. Most of the stuff on the bench is derived circuits. However, I've done heavy industrial in the past. As a control guy in the industrial space, I do work in and around some 483 phase. The biggest stuff that I've worked on somewhat regularly was 663 phase, very high amperage. We had so much amperage in those cabinets that wire wasn't good enough yet, or wasn't good enough anymore. We were literally bolting things together with copper bar. It was copper bus bar construction because the current on those conductors was pretty heavy. Know the hazards associated with it. Be comfortable with high voltage, and there's levels with that. Let's take a tube radio, right? B plus will be 250 to 450 volts, somewhere around there. A small tube amplifier, audio amplifier, you might see 500-600 volts on the B+. RF amplifiers, depending on the wattage, you're getting into the 3,000 volts. The CRTs and the scopes, the third step in the calibration process is measure the 4,000 volt supply. That 4,000 volt supply hits a doubler or a tripler, and it gets bumped to 21, 27, 28 kV to drive the anode of the tube. Not a lot of current, but it'll wake you up if you get hit by it. Was it the 7904 that blasted me with the anode? It might have been. I was pulling, the scope had been off for a while, and I thought that everything was discharged. And I was pulling the anode separator apart, and as soon as it cleared, it just jumped right to my hand. Now, from an instance, I would call it a strong static shock. I mean, it just discharged some very, very tiny capacitors into my hand. I felt it. I felt it all the way up to my shoulder. Was it dangerous? Oh, I'm glad it was off. Wouldn't have done that with it on. But, oh yeah, it woke me up. That's another thing. Don't work on tube gear tired. Once you start getting tired in the lab, I work late into the night in the lab, but there are times where I'll do computer work or something like that, but I just recognize that I am not safe to be probing around high voltage circuits until I get some sleep. So keep an eye on yourself too, because complacency is when dumb stuff happens. Oscilloscopes, electrostatic screens, you're up around 4,000 volts on the supply after the tripler, about 27 kV. The worst one, actually, for high voltage in terms of just sheer numbers is color television and computer screens. They run 125 kV, and when I was just learning some of this stuff, I kept looking around because I was like, well, there's a giant capacitor in here that's going to buzz me. I want to know where it is. And I kept looking for it, kept looking for it, and I could never find it. And it finally hit me that the capacitor in question that holds the charge in a CRT screen is the entire back side of the vacuum tube. So the inside of the tube is coated with a conductive coating. One of the brand names of it is Aquadag. The outside is covered with a conductive coating, and there's an insulator in the middle. So you have two plates with an insulator in the middle. There's the capacitor. It doesn't sound like a lot because it makes like a 9-10 picofarad capacitor, not that much, until you put 125 kV across it, and then it can wake you up pretty good if you come across that one. So flyback transformers, not a lot of current, but definitely elevated voltages. Tube RF amplifiers, lots of current, about 3,000 volts. Some of the stuff it takes to light these guys up, this is starting to get into power supplies that they came with interlocks from the factory, so the B plus wouldn't turn on when a technician was in the cabinet. So high voltage, understand high voltage measurements too, not just for technician safety, but for equipment safety. 4,000 volts will blow the scope up, blow the meter up. There's none of my meters can take a 4,000 volt input. So we have to use a high voltage probe, high voltage probing techniques. You start getting into 100x, 1000x scope probes. Actually, I have a 1000x scope probe, which is kind of wild. This is a Tech-Made, still in the Tech box, 1000x scope probe. So when this probe is put together, it's absolutely huge. This is the probe itself. The handle comes in the back, and the technician holds it here, and the measurement's taken up there with a ground lead right there. This is good for 20 kV DC continuous with a 40 kV max peak pulse. So it's a P6015 1000X, and it is a 100 megohm DC scope probe. Now, to get the isolation even wilder, it came with a high voltage dielectric fluid, which was essentially, there's an R number on here somewhere. It's a refrigerant, which this can is almost dead. 114, fluorocarbon 114. So good luck if that's empty, which it is. Good luck finding a replacement can of that in today's environment. That one's not going to be easily sourced. So the important part with this probe is to keep from here forward clean. Dust, dirt, grease, grime that gets on this body can create a voltage path where it'll arc over to your hand, and that can cause a hazard, especially when measuring 20 kV. So this isn't even good enough to measure a color CRT flyback. Need something even stouter than this. The other thing, too, is understand the derate curve on the scope probes. It's in the manual. At DC, it'll hold current all day long, or it won't hold current. It will hold voltage back all day long. At AC, the higher the frequency is, the less AC can be on the probe tip because the probe has to be derated based on frequency. And it's so, cleanliness is so important with some of the HV stuff. They even put a dehumidifier, silica gel dehumidifier, in the probe container to keep everything dry so humidity doesn't build up, soak into the plastics or anything like that. So especially dealing in the 3 kV plus range, things get a little strange. Things get a little strange starting over 1,000 volts, but the further up the voltage line you go, the weirder stuff gets, because the jumpier the potential gets. On the meter side, I did a high voltage primer, which goes into detail on how to use this and what to do with it. But this is a DC high voltage probe. This one's good up for 6 kilovolt. So same thing. The red zone, you don't hold it up here, you hold it back here. And this needs to be clean, like since I'm touching this and things like that. I'll wipe this down with alcohol before I put it away, things like that, just to clean this surface up. And I usually wipe it down before I use it to measure close to its top end. It'll take 2 kV without too much trouble. Using things near their limit is where all of this stuff becomes really important. Also, the 1000X divider probe from Tech works exactly like a 10X probe. It's 1,000 times attenuation versus 10 times attenuation. You can also get a 100X probe, which I have one of in the lab. Don't need it often, but I did need it for some CRT stuff. Essentially, whatever the scope is set to, the probe tip will have 1,000 times more voltage than whatever the scope is reading, which is how those probes work. Same thing like a 10X probe. The other thing, too, is to learn the hazards of tubes themselves. This is kind of unique to being tube equipment just because of its age, especially depending on the age of equipment that you're going to be working on, because the different eras had different problems. Tube equipment goes back to the 20s and 30s. And when we go back that far, you're going to run into beryllium heat sinks, asbestos pads. You open the radio, there'll be a pad on the bottom of the radio, has asbestos blanket on it. HP had some pulse generators that, quite literally, to get the pulse shape right, asbestos sock went over 2 of the output tubes. Well, they had an asbestos sock over these output tubes, and then they had a fan blowing it right into the room. So that can be... That wasn't good. There was some arguments about that. So you'll run into true asbestos. You'll run into PCBs in capacitors, the bathtub-style capacitors, which are oil-filled. The polychlorinated biphenyls are incredibly carcinogenic and need to be disposed of properly. The some of the other hazards you'll run into is on these 866As. These are mercury rectifiers, so everything's fine with the mercury in the tube. It's not a problem. However, if this envelope gets broken, it'll launch mercury into the room. So that is just something that needs to be known and just be aware of. The 866, the 83, I think, also has mercury in it, if I'm remembering correctly. 83 is found in a lot of tube testers. They use it as a dropper tube. And it actually has it is a mercury rectifier as well. So these guys have a similar problem, although it's not mercury, it's radiation. So these tubes are actually radioactive. These have thoriated cathodes in them. So it helps with with electron emission, gets them hotter. I am not up to the minute on my radionuclides. However, I believe the primary decay from thorium is alpha decay, in which case this is safe as long as it's in the envelope. Now, the problem is if it ever breaks or anything like that or something happens and the thoriated cathode gets aerosolized, there's a lot of don't cut, grind, saw, polish type things. But this is also true. They have thoriated welding rod too. Same problem. But if the dust ever gets airborne from the thoriated cathodes, and you breathe it in, you now have a radionuclide dust decaying in your lungs. That's where the actual health hazard comes from. A piece of paper will block alpha decay, so skin's good. Glasses envelope is blocking most of it, but the definitely don't want to breathe it. And yeah, internal radiation is just bad. So know what you're working on. The other thing too is some of these tubes, especially these guys, these bigger transmitter tubes, these take a monstrous amount of current to light. Some of these things, I'd have to look up the exact data sheet, but I think some of them need like 6 volts at like 24 amps just to turn the tube on. That's not even B+. That's just to light up the tube. So some of these are just, well, there's a burn hazard there. These glass envelopes, actually a tube can melt the glass if it's overdriven hard enough, and especially some of the bigger tubes. The envelope can actually just melt down because the tube just gets so hot. So definitely don't want to go grabbing these right after you turn them off. Obviously, there's a B+ problem there too, because these run at a very elevated voltage. Well, I'll pull up the data sheet for a VT166 and we'll see what we find. So this is not an RF transmitter tube. Actually looking it up, I believe this one is though. CR810. I'll have to check that one too. This is a half-wave rectifier. However, this is one of the biggest rectifiers I own, actually looking at the data sheet now. It takes 5 volts and 10 amps on the filament just to turn the tube on. It can then half-wave rectify 30,000 volts on the plate, which is quite substantial. So you'll know if you're walking into something that has one of these still in service. But I believe they were used in transmitters quite a bit. So everything I said about thoriated cathodes and things like that, we have an example right here. This CRC810 does have a thoriated cathode in it, and this is a transmitter tube. Nowhere near the voltage of the rectifier. However, we still have 10 amps of filament voltage to turn this thing on, but then this will do 700 watts at 2500 volts plate. So this is a significant transmitting tube. Checking the cost on some of these is kind of bonkers too when I was looking up some data sheets. So that's some of the hazards about. Couple of others is chassis. When working on chassis, depending on the era, they could be cadmium dipped. Don't want to grind any of that. Cadmium. A lot of this stuff is just rough for the lungs. Cadmium's rough for the lungs. Beryllium's rough for the lungs. Silicon's rough for the lungs. Yeah, so learn some of the hazards of the equipment that you're working on. Beryllium, don't cut it, grind it, saw it. Pretty safe to handle. The dust is what's the problem. Burlicosis would be the issue. Silicosis would be the other issue. So just some things to look up if you're curious. This is one of my capacitors that's kind of cool. You will want to look into cleaning, servicing techniques. We could tell by looking at this capacitor that there's a lot of old grease that's on here that's dried and things like that. So if I wanted to put this back into service, I would need to clean this both electrically and mechanically. Working on tube gear, you become a mechanic as much as a electrical technician. Well, there's a lot of electromechanical parts. This capacitor is a good example that need to be serviced, cleaned, things like that. Dial strings will wear out over time. Grease hardens some of the stuff. So you'll buy a brand new old stock capacitor, new in a box, and the shaft is seized. It just won't move. So there are techniques to break those loose, get them moving again. A way to validate the part too, just to make sure the plates are still the range is. How was it handled throughout time? Some of this stuff isn't even made anymore. Unfortunately, a lot of the tech scopes that I have here in the lab, which I love using, are running on borrowed time ultimately, because eventually the tubes are just going to die from hours, and they're that's going to be it. No one's making tubes anymore. So once the cathodes are done, that tube is recycle, unfortunately. So actually I have 2 576 tubes that are in that state right now. They're just high hour and very, very, very dim. And because it was a unique tube, there's no way to bring it back. So unfortunately, that is what it is. But some of this gear, especially the 576, there's no modern equivalent. So we are stuck with what we have. The other thing is soldering some of this old stuff. It's not awful, but what you'll want to do as a technician is get your soldering speed up, especially in some oscillator circuits, things like that, things that use polystyrene capacitors, a few other things. They cannot be held at too high a temperature for too long. They'll permanently change in value. So with a soldering iron, some of the it's odd because some of the joints will take an enormous amount of heat to actually start doing what they're supposed to. And then some will just go so fast, and you'll mainly run into polystyrene capacitors in oscillator circuits in the later eras. Also, understanding how, why, and when capacitors fail, and also what you can replace them with. For example, it is possible to put too much capacitance on the backside of a tube rectifier. If you do that, the rectifier turns into a fuse and will destroy itself. So know the limits of tube gear, where a silicon, well, you can put too much capacitance behind a silicon diode too. Right when you click the power button on, it dumps a whole bunch of current because it tries to charge that cap right now. And the inrush current through that diode for about a minute or two could be enormous. And so inrush current can actually burn up the rectifiers. So it's just something to be cautious of. One of the other really important things for working on tube gear is understanding, which is some of the reasons why I have some VTVMs and I have some very high impedance meters. One of the things these tech meters are actually good for is in auto mode, they're a 20 megohm input impedance. They're not a 10. The Keithley 6510 and 7500, or the 6500 and the 7510, depending on the range, they can have a 10 gigohm input impedance. Vacuum tube circuits tend to be very, very fragile in terms of biasing, loading, and things like that. There's not a lot of current available, so a lot of the supplies tend to be a bit soft. So loading a vacuum tube circuit with the test equipment can make it do funny things. So understanding that circuit loading, how you might be interfering, especially with oscillators. Hooking a piece of test gear into the equipment, you'll get it dialed in, you'll pull it off, and you'll be off frequency because the test equipment dragged the oscillator. Very, very, very common. So it's why I have a mix of both vacuum tube gear and modern gear here in the lab. I didn't standardize on just one because there's some things where the modern gear is a little bit better. There's some things where the VTVMs are a little bit better. This HP 410B, for instance, one of the reasons it's a little bit better is because it has a vacuum diode in here, and this does AC up to, I think if you have the D-rate curve, up to 700 megahertz. So I got 700 megahertz of AC. This does like 10 kilohertz. Maybe 100 kilohertz. I think might be 100 kilohertz. So even today, there are places where I need to fire up this VTVM specifically so I can take a measurement that the modern stuff can't do. So I hope that answered some questions about kind of the path to becoming a vacuum tube technician. If not, or you have anything to add, hit us up in the description below. Look forward from learning from you guys as much as I can. And I hope to see everybody in the next video. If you like the content, want more, check out the Patreon page. Patrons are running ahead from what's available on YouTube. As always, more is on the way, and I will see everybody in the next video. Bye for now.